Hello. This is the first video on probability, PB2 from the HSC General 2 course, Multi-Stage Events and Applications of Probability. A random mathematical fact for you. Did you know that probability originated in the 17th century when two mathematicians, Blaise Pascal and Pierre de Fermat, were trying to split the pot, the money, in an unfinished gambling game? That might help you out at a trivia night at some stage. When faced with any probability question, we have a range of tools in our toolkit that we can employ. In this video, we are going to sharpen some of the tools that we already have in our kits, and over the next few videos, we'll acquire the tools we need to tackle any job. The first tool I've pulled out is the SAW of basic probability. The key terms you were introduced to last year that are expected knowledge. Let's recap. An outcome is the result of an experiment or game. What could happen? If we rolled a standard six-sided dice, one outcome is to roll a 6. If we were watching a footy game, one outcome is a win. The sample space is the list of all possible outcomes. For our die, it's all numbers 1 to 6. For our footy game, what are the possible outcomes? You have a win, a draw, or a loss. Normally, the elements of the sample space are listed in curly brackets. An event is a group of one or more outcomes. If our event was looking at the prime numbers when rolling our die, what are the relevant outcomes? They are 2, 3, and 5. If our footy team needs to avoid a loss to get through to the next round, we're looking at the outcomes of a win or a draw for that event. The theoretical probability is what should happen. It is a ratio of the number of outcomes that satisfy the event over the total number of outcomes in the sample space. So for our prime numbers, the probability of rolling a prime number is 3 prime numbers from numbers 1 to 6 over a total of 6 outcomes in our sample space, so the probability is 3 in 6. Equally likely outcomes have the same chance as occurring. If you roll a fair die, all numbers have an equal chance of being rolled. With a game of sport, such as footy, it is not so common to get a draw, so we know that the 3 outcomes are not equally likely. We'll chat more about this in class. The probability of an event ranges from impossible, or a 0 chance of occurring, through to certain, or a 100% chance of happening, and everything in between. The probabilities can be expressed as a number between 0 and 1, as a decimal or a fraction, or as a percentage between 0 and 100%. If you need these notes, you can pause the video and copy them from the following screen. Complementary events. The not event, the probability of the event not occurring. In our example before, I spoke about the footy team who needed to avoid a loss to get through to the next round. They needed to not lose. Often, complementary events are referred to as the opposite event, but this can be misleading. The opposite of not losing is winning, or is it? In probability, the complement of not losing is either winning or drawing. It's not just the win. Think about rolling a dice. The probability of rolling a 6 is 1 in 6. So the probability of not rolling a 6 is actually the probability of rolling a 1, 2, 3, 4, or 5, which is 5 in 6. A special property of probability is that the probability of the event and its complement add up to 1. Or, rearranged, the probability of the complementary event is 1 minus the probability of the event, where P of E is the probability of the event and P of E dash is the probability of the event not occurring. A quick example. If you're feeling confident, pause the video, get your answers, and then compare them to the work solution. The example says, a jar contains 12 red, 7 yellow, 8 white, and 13 black jelly beans. If a jelly bean is selected randomly from this jar, express as a decimal the probability that it is A, green, B, black or white, C, not red, and D, black, yellow, or red. The solution. To work out the probability, we first need to find the total number of jelly beans. That is, we need to add up the values of the number of jelly beans of each colour. We've got 12 red, 7 yellow, 8 white, and 13 black jelly beans, giving us a total of 40 jelly beans. The probability of it being a green jelly bean. As there are no green jelly beans in the jar, that means that the probability is 0 out of 40, or just 0, that is, that it is an impossible event. The probability of drawing out a black or a white jelly bean means that we need to look at how many black and how many white jelly beans there are. There are 13 black jelly beans and 8 white jelly beans, which means that we add those two up, and the probability of it being black or white is 13 plus 8 out of 40. 13 plus 8 is 21, so it's 21 out of 40. And we can convert that to a decimal because the question asks us to express it as a decimal. Using our calculator to do that, we get the answer of 0.525. Part C. Find the probability that it is not a red jelly bean. Not red is the complement of it being a red jelly bean. So that means that we use 1 minus the probability of being red. The probability of it being a red jelly bean, there's 12 out of the 40 jelly beans are red, so that means that we've got 1 minus 12 out of 40. That is equal to 28 out of 40, which we can simplify by dividing the top and the bottom by 4, giving us 7 out of 10, and then expressed as a decimal, that answer is 0.7. The probability of it being a black, yellow, or red, with there only being 4 colours in the jar, this is the same as finding the probability that it is not a white jelly bean. Probability of it being white is 8 out of 40, so we subtract that from 1 to find the probability of it not being white, which gives us the answer of 32 out of 40. If we add up the probability of the black, yellow or red, that is the 12, the 13 and the 7, 7 plus 13 is 20, 20 plus 12 is 32, and so we get the same answer whether we use complementary events or whether we just calculate the probability of those 3 events occurring. 32 out of 40 can be simplified to 4 out of 5 because we can divide both numbers by 8, and then turning it into a decimal we get the value of 0.8. We've talked about the theoretical probability being what should happen in an ideal world. The experimental probability is what has happened in an experiment. The experimental probability gives us the relative frequency of an event, the number of times it has occurred over the number of trials conducted. That is, the frequency of the event over the total frequency. Here is the theoretical probability as a comparison, the number of favourable outcomes over the total number of outcomes. Here's an example of rolling a dice 24 times. We can see that the 1 occurred 3 times, the 2 occurred 4 times, so on and so forth. We don't know how many 6s there are, but we do know that we rolled the dice 24 times. So if we add up the values that we do know and subtract that from 24, then that will give us the number of 6s that were rolled. So 24, take away 3 plus 4 plus 5 plus 1 plus 6. 3 and 4 is 7. 7 and 5 is 12. 12 and 1 is 13, plus 6 is 19. So we're doing 24, take away 19, which gives us a value of 5. So there were 5 6s rolled. The relative frequency is looking at the number of times that it occurred. So we know that we had the number of 6s over the total frequency. We had 5 6s over 24 rolls, which gives us in decimal form 0.20833. Unless the question states to answer in a particular form, you can answer either as a decimal, a fraction, or a percentage. It's up to you. The third part of this question asks us which number's experimental probability matches the theoretical probability. We know that the theoretical probability of each of these numbers occurring is 1 in 6. To find the theoretical probability after we've rolled it 24 times, then we multiply that theoretical probability by 24, which is 1/6 times 24, which is equal to 4. By consulting the table, we can see that the number 2 occurred 4 times, so the number 2 has the experimental probability matching the theoretical probability. Sample spaces for multi-stage events can get complicated. A recap: a multi-stage event consists of 2 or more events occurring together, such as rolling 2 dice or tossing 3 coins. When determining the sample space, we may use tree diagrams, tables, or lists to identify all possible outcomes. The lists are good, a very small number of items. Tables are good when there are 2 concurrent events, such as rolling 2 dice or tossing a coin and rolling a dice. Tree diagrams are a good systematic way of listing all outcomes in a multi-stage event because it allows us to see each stage at a time. Let's do a quick recap of how to use a tree diagram. If we toss a coin 3 times, what are the possibilities? We can see here that each branch of the tree indicates each stage of the experiment. On the first toss, it's possible to get a head or a tail. On the second toss, if we got a head the first time, we can get a head or a tail the second time. Likewise, if we got a tail the first time, we can get a head or a tail in our second toss as well. On our third toss, we can get a head or a tail for each. With the completed tree diagram, it is good practice to summarise each of the branches at the end, so it is easy to assess. Abbreviations are fine. If we follow along this branch here, we see that we get head, head, head. If we follow along the next branch, we get a head, and a tail. Following along the next one, we've got a head, a tail, and a head again. And we can see that if we go down each of these, we simply write the abbreviation of each of the outcomes next to the final one, so we can easily refer to those to answer any questions we may have. That concludes the first video where we recapped some of the concepts from the preliminary course. We'll be back soon.